and can I add my welcome to those of you joining us for this session. Could I ask that whilst I'm speaking that everyone mutes their own microphone, please, because otherwise with background noises in everyone's own place, it starts to sound like we're in a washing machine. So if you could mute until you want to speak, that would be really helpful. Thanks. Excuse me. This is Welcome to Pearson, International Advanced Level Physics. This online training is designed for teachers who are new to delivering international advanced level physics, this specification. The training is actually comprised of 3 standalone modules which are booked separately. This module focuses on teaching the course and will hopefully give you an understanding of the content of the qualification and how to cover it, something about course lesson planning. Module 2, which happens tomorrow at the same time, is looking particularly at the assessment and preparing students for it, and a brief overview of support from Pearson that's available to teachers. My name's Keith Penn. I've been a teacher of science to GCSE, all sciences, and physics to A-level for 33 years. I now work as a lead science trainer for Pearson. I'm joining you today from fairly nice, but a little bit grey morning just outside Cambridge in the southeast of the UK. I taught for 33 years in London and the southeast of England, and as I say, I'm joining you from just outside Cambridge. I hope you got slightly better weather than I have. Okay, let's have a look at what we're going on to do. In this training then, we'll identify how the qualification is devised. We'll review the content of the qualification, explore a little bit about how to plan the course and lessons, gain an understanding of the assessment of the qualification and how to prepare students to do well in those assessments, and to look at the support that's available from Pearson. Okay. So first of all, welcome to the company, to Pearson Edexcel. There may be a number of reasons why you're joining a new to Pearson, Welcome to Pearson course. It may be that your school or centre has just taken on this specification, previously delivered a different one. It may be that you yourself have recently changed school and you're now in a school which is delivering this spec and need to find out more about it. Or you might yourself be new to teaching, all the valid reasons for joining a Welcome to Pearson course. Pearson Edexcel is the world's leading learning company, and as the UK's largest awarding organisation, we believe well placed to provide qualifications which are aligned to the British education system. Our international heritage stretches back over 150 years, and today we partner with schools, universities and employers worldwide, offering world-class, globally recognised qualifications to over 3.5 million students every year. We're a trusted and recognised qualifications partner to 6,500 schools, college and employers across the world, and we mark over 10 million exam scripts on behalf of the UK DFE each year. We operate in 70 countries worldwide. Let's have a look at the specification we're talking about at this session. I'll occasionally say this morning or later this morning, and I do apologise for that because I am conscious that some of you are joining us from places where it's no longer morning. You've already passed the midday, and apologies for that. Here it's just after 9 o'clock in the morning. Specification is the main document you need to teach the course. It outlines the aim of the course, the content you must cover, and all the information that you need about assessing your students. And a copy of this document is in your download pack, which Phil mentioned a short while ago, and you can also download it freely from the website. There are also sample assessment materials. When a specification is first launched, it's a really useful document because it provides examples of the type of question papers. There are now several series of live exam papers with real exam questions to look at, so it's arguable that the real papers become a more important resource than the sample assessment materials, but as I said, they're useful in an assessment when a specification is first launched. So, from the specification, the International Advanced Subsidiary and Advanced Level in Physics are modular qualifications. The content is relevant for learners who've achieved GCSE or IGCSE in physics and who want to study the subject at a higher level. The assessment consists of 3 written papers at advanced subsidiary level that are externally assessed, and the full A level consists of 3 further written papers that are also externally assessed. And learners develop their knowledge and understanding of physics by applying the concepts in this specification to a range of different problems that include a variety of contexts. And these problems will require the application of mathematical skills. Learners will also develop their practical skills. So the AAS can be claimed on completion of the 3 IAS units, and the full A level can be claimed on the completion of all the units, the IAS and the IA2 units. The content covers major topics that you'd expect in any advanced level physics qualification, including mechanics, materials, waves, electricity, fields, thermodynamics, radiation, particles, oscillations, cosmology. The spec includes 16 core practical activities, and this is the minimum number of practical activities that learners will carry out. Centres are encouraged to enable learners to carry out additional practical activities to further develop their practical skills. We'll be having a look at in a bit more detail at those. So using the spec, the compulsory content section gives an indication both of what needs to be taught and the level to which it needs to be taught. The sentence on assessments here is important. It means that questions can and will be asked, which are set in a context that's different to that in which the knowledge and understanding was first learned. Students need to develop the confidence to be able to apply their learning to different unfamiliar contexts. Hence the comment here about a good range of examples. It would not be possible to predict or to prepare students for every possible context which examiners might come up with. The key is to expose students to a wide enough range of opportunities to realise that they can successfully apply what they know and understand in other contexts. This is a page from the content section, actually in 1.4 materials, and it indicates how the core practicals are shown. You can see as you look down the, let me just click where there's an arrow here, you can see down the sheet there, the core practical is in bold print, and it actually says clearly core practical in capitals. Use a falling ball method to determine the viscosity of a liquid. So the core practicals are clearly identified. There'll be more on the assessment of practical skills later on in this presentation. Slide also shows how the specification content pages give more information. For example, identifying which formulae need to be able to be used rather than simply remembered. Here's a summary from the specification of the unit breakdown of the IAS and the full advanced level qualifications. It also shows how the specification content pages give more information. For example, identifying which formulae need to be able to be used. So looking at the IAS, the qualification consists of 3 externally examined units. It's the first half of the full A-level qualification and consists of units 1, 2 and 3. It can be awarded as a discrete qualification, so you can stop at the end of 3 and cash in an advanced subsidiary, or it can contribute 50% towards the full advanced level. It includes questions that target maths at level 2 or above. Overall, a minimum of 40% of the marks across the paper will be awarded for maths at that level. Looking at the full A level, that consists of the full 6 externally examined units. The IAS units 1, 2 and 3, and 3 further units 4, 5 and 6. Students wishing to take the international advanced level need to complete all 6 units and assessment in them. It too includes questions that target maths at the same level, and again a minimum of 40% of the marks across the papers will be awarded for maths which is at that level, as you'd expect in a physics qualification. If we look in a bit more detail at the units themselves, here's an overview of the 3 units which form the IAS units and their assessment. So Unit 1 on mechanics and materials and Unit 2, waves and electricity, are 2 content units, and you can see they're both examined with an external written exam, 1 hour 30 minutes in length, which accounts for 80 marks each. So by themselves, they account for 40% of the advanced subsidiary or 20% of a full A level. And in both cases, the papers include multiple choice questions, short open, open response, calculations, and extended writing questions. And in the module tomorrow at the same time, where we look at an assessment at more detail, I'll be showing you examples of those sorts of questions, and we'll have an opportunity to look at some exemplars and how the mark scheme works. Unit 3 is slightly different. It's also an externally assessed written exam. It's slightly shorter, 1 hour, 20 minutes, and accounts for 50 marks, which is 20% of the AS or 10% of the full advanced level. And Unit 3 is assessing the practical skills, the knowledge and understanding from experimental procedures and techniques that have been developed while students were doing practical activities as they studied Units 1 and 2, the 2 content modules. The paper also includes short open, open response calculations and extended writing questions, no multiple choice questions in the Unit 3 practical paper. If we look at the 3 units in the IA2, which combine with the 3 we've just looked at to make up the full A level, you can see there's a similar sort of pattern. Units 4 and 5 are content modules, further mechanics, fields and particles in Unit 4, and thermodynamics, radiation, oscillations and cosmology in Unit 5. They're also assessed by external papers. All the papers are externally set. There are no practical exams or assessed practicals in the laboratory, no coursework in this subject. So they're externally assessed written exams, which are 1 hour, 45 minutes long. Each account for 90 marks. And as before, they're 40% of the IA2 or 20% of the full advanced level. They also include the same range of questions as we saw in Units 1 and 2. Unit 6 is sort of similar to Unit 3 in that it assesses knowledge and understanding of experimental procedures and techniques which students have developed in Units 4 and 5, and of course also those which they developed in Units 1 and 2. As before, the paper includes short open, open response, calculations and extended writing questions. Again, no multiple choice questions in the practical paper, in the Unit 6 paper. It's worth highlighting the sentence which appears again and again in these books. Students will be expected to apply their knowledge and understanding of content and practical skills to familiar and unfamiliar situations. And the applying it to unfamiliar situations is a thing that students struggle with. It's something we need to focus on. Okay. First activity that we're going to do during this session, you'll need to consult your copy of the specification, which, as Phil said, is downloadable from this event, or you may already have a copy downloaded. So I'll give you a couple of minutes to try and find answers. Here's a question, part of a question from an exam paper. And what I want you to do is not answer the question, but tell me in the chat, please, in the meeting chat, which part of the content do you think is being assessed? Which specification point? So you can give me a number, if you like. Which part of the content, which specification point is being assessed by this question? You see the question, Kevlar is a modern lightweight material. Due to its physical properties, Kevlar is being used to replace nylon and steel in many applications. The stress-strain graphs for Kevlar, nylon and steel are shown below. And there's the graph. When pulling a heavy load, Kevlar cables are now often used instead of nylon cables. Explain 2 advantages of using Kevlar in cables compared to using nylon. So could you, in the meeting chat, suggest which specification point or points do you think are being assessed by this question? And I'll stay quiet for a couple of minutes while you scour through your specification and put the number in the meeting chat. Okay, we've had a first bid, 1.4, specification 0.30. I'll wait for more to come in. It's certainly materials. Okay, another one saying 1.4, but 28, 29 and 30. 2.2, young models, modulus, I guess, yeah. Yeah. And I'll put you out of your misery. The answer is topic 1.4, materials, absolutely, in unit 1, materials and mechanics. So 1.4, it's actually tackling specification 0.30, which specifically says be able to draw and interpret tensile or compressive stress strain graphs and understand the term breaking stress. And it's absolutely tackling the middle part of that. They're being asked to interpret stress strain graphs in this question. Yeah, so well done. And in fact, every exam question tackles one or more specification points. I mean, sometimes people will look at the exam papers and say, such and such a thing was not covered in exactly that way. Could I ask you to mute your microphone, please, Ariana? Thanks. Sorry. Sorry, people will sometimes look and say, that didn't really tackle the question in the way it appeared in my textbook. And the reason for that is that the examiners do not in any way refer to textbooks when they're setting questions. The thing they use, their Bible, if you like, is the specification. They will only be asking questions based on specification points. So if you ever want to know how a part will be specified or will be what depth it will go to, the key to that is what it says in the specification, because that's the document the examiners are required to use to set the questions. They'll be asking questions based entirely on what it says in the specification. Okay. Here's a content overview. This is really an opportunity just for you to get an idea of the topic coverage within the specification. You might want to spend a moment just considering what's been included and also what's been left out compared to other courses that you might have taught previously. Okay, so in Unit 1, as the name suggests, it includes mechanics and materials. Unit 2, waves and the particle nature of light and electric circuits. Unit 4, further mechanics, electric and magnetic fields, nuclear and particle physics. And Unit 5, thermodynamics, nuclear decay, oscillations, and some astrophysics and cosmology. And in the Unit 3 and Unit 6, it's as it says there, students are expected to develop experimental skills and techniques by carrying out a range of practical experiments in Units 1 and 2, and for Unit 6 in Units 4 and 5. And as it suggested earlier on, students are quite hampered if they only do the core practicals. They really need to have a range of practical experiences so that they really get used to developing those experimental skills, devising some experiments of their own, getting used to working scientifically, part of physics. Okay. Okay, this is what I want you to do. Choose one topic or part of a topic from the physics specification. Plan the order in which you would teach that topic. In other words, how would you start? What would you go on to? I don't need a full teaching plan here, but think of a topic and think, what are you going to start with? What will you go on to next? So you might just put 2 or 3 parts of the topic. Which order would you teach the parts in that topic? You could start with the mechanics one that we've just been looking at, if you like, or you could choose a different topic altogether. So you might need to put in your answer both the topic you're talking about and then which parts you would, a teaching order for that section. If you like, you can put a reasoning about why you've chosen that order, why you start with one thing, why you go on to the next. Okay. Okay, I'm seeing a number of comments saying that you haven't received the materials or can't find the materials. If you go onto the tab on your screen where you control your mute and stop video and so on, but go right along to the right-hand side, it depends how shrunk your menu is, but sometimes it's on more, but you're looking for a tab which says resources. In the three dots which says more, if you go down to where it says resources and clicks on that, you can see three tabs across the top of that saying links or documents or speakers. I'm doing this now live myself. If you click on documents, it opens up two documents. The first one of those is the specification, the one that we're looking at. And the other one is the sample assessment materials. So both of them are attached to the resources which are with this presentation. You can also access them freely available online. If you go to the International Advanced Level Physics page on the Pearson website, so you can type into a search engine such as Google or any other good search engine, a combination of the words Edexcel and International Advanced Level. Subjects are laid out in alphabetical order, so you can scroll down to physics. So when you're on the physics page, the advanced level physics page, you can see teaching and learning materials, exam materials, specifications, and so on. You can find the specification and past papers and lots of teaching and learning materials. In fact, all the materials that I'm referring to over the next couple of sessions are available for free download from there. So you can either download them from the resources linked to this Zoom, or you can go to the Pearson Edexcel physics homepage and download them from there. I hope that helps. Any comments on the question which is on screen? Remember, I'm asking you to choose one topic from the physics specification and to tell me the order in which you would teach that topic. What would you start with? What would you go on to? What would you do next? I'll stay quiet for a couple of minutes while people put in into the chat suggestions for answers to that. Remember when you put it in the chat that you need to, there's like a blue symbol next to 2 on the direct message where you can choose who you're sending the message to. You need to select everyone in meeting so we can all see the answers there. Otherwise, it's not really discussion. It's a lot of private text from one person to another. So make sure you choose who you're sending chat to everyone. Thanks. I'm not seeing any suggestions yet. Have I made the question clear? Sorry, I want you to choose one part of the special. Oh, there we go. There we go. Thank you. It's starting to come in. Starting with Hooke's law, presumably with springs, that kind of thing, elastic bands, then going on to stress strain curves. Yeah, okay. I'll leave it till a few other people put suggestions in as well. Thank you, Jean-Paul. So Shabam, let's put topic 1.4. We call density from GCSE, including displacement, can, practical. Oh yeah, the Eureka can, yeah, for regular and irregular objects. Good. Calculations to cover specification point 23. Then going on to drag, laminar flow and turbulent flow, Stokes equation, and then the core practical. Okay, great. It's good. It's good. Any other suggestions? Okay, Robert saying, I always start with some real life examples and questions. Okay, okay. Okay, I'll move on. I'll leave the chat open for other people to put suggestions in. The point I really want to make, and that's kind of coming up from answers we're getting already, which is great, is that we need to consider the idea that we need to consider what's the most effective and logical way to present a topic. The answer isn't, it isn't necessarily the way it appears in the specification. So although there's a sort of logical order of material or information within the specification, you're not required, or is it not even suggested, that you teach in that order. You don't have to go to specification point 1 and then 2 and then 3. It's not designed as a teaching order. And there are good reasons sometimes for it not to be that order. And there isn't a right answer for that. It will vary from from one cohort of students to another. In some ways, Shivam Kapoor's answer there has hit the nail bang on the head, because your students aren't coming to this cold. If they're doing an advanced level physics, they've already learned some physics at GCSE, at Key Stage 3, science even before that. So they're coming with some previous knowledge, some prior learning. And a good starting point is to identify that prior learning. So if we're starting a new topic, I mean, I always find it useful to try and recap on what students already know, perhaps get students to draw a concept map or a diagram or write down things that they already know. It gets them into the frame of mind of saying, okay, this is the area of physics that we're going to be looking at now. But it also identifies what students already know, and crucially, what they don't know, where the holes are or misunderstandings from earlier learning. And that can be really good information for a starting point. Okay, this is where we are now. We'll move on to learn that. So I think it can be really useful to do some recall. You're not trying to go back over everything they've learned before, but just getting students back up to where they were in their prior learning on this topic. Because there's this idea of a spiral curriculum, isn't there? Like a spiral staircase. Each time you go around the spiral, you follow the same set of courses, but you're moving higher up each time. So every time they come back to the same topic, whether that's electricity or waves or whatever, they're adding to learning that they had the last time they were in this position on the spiral. And so they're learning in each time. So it's sometimes useful to bring them back to where they were, find out what they understood and what they didn't understand, and use that as a starting point. And that will be different from one group to another. Some students will have misunderstood some things. Other students will be well ahead of that, and you need to start somewhere else. Clearly, in any topic, there are some bits that have to come before other bits, because it kind of builds within the topic itself. You know, you got to learn the basics before you can move on to the advanced applications. But there isn't one straight way through it. It's not necessarily, not even the way in which it appears in the specification, nor necessarily in a textbook you might be using. The textbook, the writer of the textbook will have had an idea in their minds of the reason they put the chapters in that way, but it's not necessarily the best way of teaching for your group of students. So I'm suggesting it is something that we as teachers need to consider each time. What's going to be the most effective way to present this topic? What we're going to start with? When are we going to bring in these examples? And that will be different from group to group and from teacher to teacher. Let's have a look at experimental skills. In order to prepare students for the assessment of experimental skills, that's units 3 and 6 in the exams, it says within there, centres should give students opportunities to plan experiments, implement their plans, collect data, analyse their data, and draw conclusions. Experiments should cover a range of different topic areas, and require the use of a variety of practical techniques. The document you can see there is also downloadable from the physics website, from the Pearson Edexcel International International Advanced Level Physics website. It's called the Physics Practical Guide. This is the teacher version. As the name suggests, there's also a practical guide student version. And the only difference between the two is that the teacher version has the answers to the questions to aid learning within there. Strongly recommend that you download this practical guide before you deliver any core practicals for the specification, because there's invaluable information in there. We'll have a look at it. Okay, but strongly recommend that you download this guide. How do the core practicals cover practical skills? As long as you follow the program of core practicals, you'll automatically cover the standard techniques and apparatus that students are expected to know and reproduce in their exams. However, every time there's a series of exams, the examiner for each subject produces a report on those exams, what students did well, what they didn't do so well, some examples of students' work, and it's regularly repeated within those reports that students who do well in units 3 and 6 are usually those who carried out a range of practicals. So you should aim to complete more than just the core practicals. It really shows when students have had a wider and more rounded experience of experimental procedures within the laboratory. So this is an extract from the teacher practical guide that I just mentioned. It's an invaluable resource. Please do download it. The core practicals are part of the specification, and the students are expected to know them for the exams. Students can use different methods and techniques to those stated, but they will still need to know and understand the methods that are stated in the core practicals. So as I mentioned, we'd recommend that you did other practical work as well as the practicals specified. They need not all include expensive pieces of apparatus. Any practical work that your students attempt, not just the core practicals, will develop their practical competency. Because, and I know I repeat this several times really whenever I'm training, I think the key to what students are doing in an experiment is not what they're doing, but what are they learning? It's a change in focus for us as teachers really, not what a student's going to do in the experiment, but what are they learning? Which skills are they learning? Which skills are developing, which they can apply to other situations? So let's have a look at teaching practical skills. The next few slides that I'm going to share with you include feedback from examiners from those reports that I mentioned that come after each series. These include feedback from examiners specifically on how students have coped with the assessment of practical skills in papers in the papers 3 and 6. And we'll use that feedback to consider the implications for teaching and learning in practical skills. So I'm going to share with you what examiners have noticed, and in a moment I'm going to ask you what are the implications for how we teach these sorts of lessons, practical skill lessons, experimental lessons, investigations. Okay, so what our examiners have noticed. So these are collated summary comments from the examiner's report on the exam for content, units 1 and 2. Many candidates showed a good progression from GCSE to A-level with prior knowledge extended and new concepts taught and understood well. That's good news. Candidates found the length of some of the calculations to be challenging, often missing out key steps, therefore only scoring 1 or 2 marks for interim steps. The new regions of the specification were answered as expected, if not better. So some good news in there. It was the problem-solving nature of some of the questions, as well as the requirement for explanations in an unstructured setting, that many found to be challenging. Students are always challenged by a sheet of blank paper where the question isn't laid out in little parts, as it were. If there's an extended writing piece, physics students struggle with that. The main challenges were on questions requiring more application. Candidates who had a sound understanding of the physics involved didn't always demonstrate this in their response due to a lack of precision of the language or terminology used, and some missed exactly what the question was actually asking. While the mathematical ability seen was strong, application to the context was not as expected. So that's an area of concern. And Unit 3, for this paper, the topics included materials, waves, and particle nature of light. As understanding of the core practicals is assessed by the Unit 1 and 2 papers, the practical context met in the Unit 3 paper may be less familiar. However, it's the skills rather than the details of the practical that we're assessing. I think that's a really important sentence, because students often think what they have to do is remember what they did in the core practical, and that they'll be asked to regurgitate that in the exam on the core practicals. And no. What they're asked to do is apply the skills they would have learned during those practicals into different situations. So it's not just remembering what happened, but why did I use this technique? Why did I use this piece of apparatus? What happened here? How can I apply that to a different situation? There were many questions that would be familiar for candidates, but there are some questions where performance would suggest they were unfamiliar with the practical skills. I think that's a polite way of the examiners saying it's as clear as day when you read a student's exam paper whether they've done the practical work or not, and sometimes they clearly haven't. Understanding of keywords such as resolution and command words such as describe how proved a challenge to candidates at the lower end of the ability range. At all ability levels, there were some questions where candidates answered in generic terms rather than being specific to the particular practical described in the question. An example off the top of my head for that is when students are asked how they could improve the safety aspects of an experiment. A number of students will always say, wear safety goggles, wear a white coat. It's just too generic. What they're asked to do is look at the particular practical. What are the dangers in this experiment? How can I minimize those dangers? Not just how can you make practicals generally a bit safer? So, sometimes it will be wearing goggles, but that's not the general answer to every question in that way. So it's saying, look at the particular question they're looking at and think what's specific to that. So here's the question I promised you. What are the implications for teaching and learning arising from the feedback from the examiner's report? So I'd invite you to put in the meeting chat, please. Are there any implications for how we teach, for our teaching and learning, particularly in experimental lessons, in practical lessons? Are there any implications which arise from that feedback about what students did well, what students didn't do so well? Whilst you're answering that, I'll go back to the previous page just to remind you about what examiners said specifically about Unit 3, but I'm still asking you the question, what are the implications for teaching and learning arising from this sort of feedback? In other words, how should you and I, as teachers of advanced level physics, adapt what we're doing in experimental lessons to address some of these issues that examiners have noticed? I'll stay quiet for a couple of minutes while people put suggestions in. Plenty of time remaining. We're almost about halfway through the material, and plenty of time left. Okay, started to get comments in. Thank you, Robert. Watch out for the command words. Absolutely. The command words are absolutely crucial, because sometimes students miss the command word and answer a question that hasn't been asked, rather than answering the question that has been asked. And even if the answer they've given has got completely correct physics in it, if they haven't answered the question that's asked, they can't get the marks for it. And the command word is key to that. Students need to think critically about the method. For example, why does one piece of equipment offer greater accuracy than another? How could we improve the accuracy of investigation? Yeah, so students would therefore need to actually see accurate and inaccurate pieces of equipment rather than just following a given method. I think you're absolutely right. I think there was a time, I'm old enough to have taught through various decades of physics, and I think there was a time where we kind of treated physics experiments a bit like a cookery lesson. You know, you gave them the recipe and students followed step 1, step 2, step 3, and at the end the law comes out or whatever. That's not what scientific practice is like at all. It's meant to be finding out things, using the techniques to discover things we didn't previously know. So students, you know, people are doing a science experiment when they check why the bulb has gone off in their sitting room. You know, you turn the switch on and off, you change the bulb, you know, you're carrying out changes to the situation and finding out whether it's the bulb or the switch or the power's gone off. You're doing a science experiment, and it's using techniques to find out answers to questions that we didn't previously know the answer to. And students need to be able to apply their learning to different situations. So it's absolutely right. Students need to know what's the right piece of apparatus to choose for this context. What am I trying to find out? How do I isolate the thing I'm trying to find out from all the other variables that could affect what's happening here? So students are understanding the method rather than just following a given method. So absolutely right there, spot on. Learning skills rather than details and using command words being specific to question. And I think the key to some of this is getting students to talk more. I think in experimental lessons, particularly when I'm observing people doing science experiments, I really want to see the students talking more than the teacher, because it's in that talk that students are sharing ideas and thinking out loud and sorting out knocking the rough edges off their learning, as it were. They need to be talking about, why am I doing this? Why have I done that? What do I expect to find? Was this surprising? All these sorts of questions. This is what I was trying to find out. This is how I did it. It went well in this way. It didn't go so well in this way. And with discussions between students who've all done same practical or similar practicals, discussion between them about what worked, what didn't work, why it didn't work. That's where the learning takes place. Because if students can express these ideas orally, they're much more likely to be able to express them in writing later on in an exam situation. It's particularly true for those of our students for whom the language they're doing the exam in isn't their first language. They need to develop and often the language of physics isn't anyone's first language. They need to be able to practice using these language skills, the specific terminology, the real meanings of the words as we use them within physics. They need to practice these by having conversations using them so that they can use them appropriately in a science exam. So it's really important that students don't just do the practical in glorious isolation and silence, but rather that they talk about them. Why are you doing that? Why are you doing that? Explain to me why this worked. It's really, really good if students in a group, let's say you've got several students or groups of students, can be doing different parts of the practical or doing the same experiment in different ways. So then they've got something genuinely different to share with the rest of the group. Anything we can do as physics teachers to encourage our students to explain what they're doing and to talk about what they're doing is absolute gold dust in terms of their learning, because whilst they're explaining it, other people are learning from what they're saying, but they're learning too, because they're putting their thoughts into words which express their learning, and that's how they will remember it. They'll remember it in a way that they can then write it down in a exam situation later on. So I think it's essential that the practical lessons include lots of opportunity for students to talk about what they're doing. Learning skills rather than details, using command words. Yeah, I said that, didn't I? It's the skills that are assessed in Unit 3. Absolutely right. Yeah, that's right. The Units 1 and 2 and 4 and 5 are sort of looking at their knowledge and understanding, but in Units 3 and 6 papers, they've definitely been asked about these transferable skills, transferable from one experimental situation to another. Thank you for that. Okay, let's move on. That was the question. Anything I missed from that? Yeah, I'll just emphasize again, I apologize if I'm over singing this song, but it really is important, I think. there are several comments within these exam reports and all exam reports that relate to students being able to apply learning from one context to questions which are set in a different context, because again and again that's highlighted as the thing which students really struggle with. So it's important that students have, wherever possible, carried out the core practicals and other experiments for themselves to be able to answer the exam questions which are based upon them. Okay, content overview. We had a look at what content is in the various units. The question I want to look at is, how do I make sure I cover all the content? There's nothing more frightening for a teacher, and it's a real danger for someone who's teaching a specification for the first time, no matter how experienced we are as teachers. Really frightening when you get towards the exam and suddenly realise there's several topics still to cover because we spent so much time covering the first few topics in enormous depth that we didn't leave enough time. So it's really essential not just to plan lesson by lesson, but also to plan out the course, so we have an overview, a calendar, if you like, of where we'll get at each stage. Obviously, you can drift from that and adapt it, but what you don't want to do is get to, you know, Easter term of the final year and realise that we've still got half the work to do. So, in addition to the specification, there are other resources that are freely available on the Pearson website. You can download from that same web page I mentioned, which are to help physics teachers plan their scheme of work. The document that's pictured on the left here is the Getting Started guide for this specification. On the right of that is the course planner, and down at the bottom right-hand corner, the scheme of work. All of these documents, as I say, are freely downloadable online from the website. The course planner and the scheme of work provide a useful starting point for matching the programme of delivery to the time that's available within your school or centre, because every school has its own peculiarities of how long a lesson is, how many lessons you get a week, how many weeks per year. You know, it varies both from country to country and also from school to school. So you need to match what's required from the course to your particular peculiarities of timing, number of lessons per week to deliver the subject. Here's a screenshot of the first part of the scheme of work model. The model scheme of work gives one way of approaching the content so that it's all covered during the time available. Reminder, this time will need to be adjusted to fit your school's timetable and the number of contact hours per week, and also, of course, the time period over which your school delivers the whole course. I will say a rider to this, and it's a caveat, you know, it refers back to what we were talking about 30 minutes ago. The order of topics in the specification and in this course planner are not intended to suggest that this is the only order or even the best order in which to deliver the content. It's one order, but you'll think about which order is the best way to deliver each topic, and that's the best order for you. You need to, and because these documents are all provided in Microsoft Word or Excel documents, it's very easy to cut and paste them and put them in a different order. So you can continue to use the content, but mix and match them in the way that you want to. You don't have to, please don't use it as a sort of, what's the word, a restricted way. Please don't let it restrict the way in which you teach. You can adapt it as much as you like. It's not meant to be a shackle. Okay, so you can see it suggests weeks here, what prior learning students would have had, the context of lessons, the content of lessons rather, and some teaching suggestions, what activities might take place in the lessons. And there's also the reference to the specification points in there, which would be covered. So say it's a useful way of looking at, and you'll want to either amend it or adapt it or start with one of your own. But I think it's essential that you plan out a scheme of work so you know what you're going to cover over the whole course and for each topic or for each term. I want to ask you, how do you plan your individual lessons in physics? So do you, for example, have a common lesson structure as a starting point? And if so, are there any ways you might need to adapt your method of lesson planning to deliver this specification? You might have a common lesson structure which is laid down by your department or by your school, or you might have one that you found is useful for yourself. I'll just give a few moments for people to put in the chat room what method you use. Which ways do you use to plan your lessons in physics? Do you start with a blank sheet of A4 paper? You know, anything will go? Or is there a sort of structure there, a sort of framework that you build your plans into? Are you required to submit your lesson plans for someone else to check, or is it entirely down to you? Do you have autonomy with that? So how do you plan your physics lessons? We won't come up with a final answer to this, as it were, but it's really useful that we have an opportunity to share ideas and find out about what works and what doesn't work. Okay, we submit a unit teaching plan to the director for approval. Okay, yeah. I mean, that varies enormously from college to college or school to school. I think it's useful that there is a pro forma. It varies who will check that or whether anybody checks it, but I think it's useful to have a suggested plan. I wonder if that's an outline teaching plan or whether it's sort of detailed, whether you have to say what you're covering lesson by lesson. Yeah, there are 19 people on the call at the moment, so I'm expecting some other suggestions here too, some other answers. Okay, Shubham said common lesson structure at GCSE that is often contained to the hour, but A-level content may need to be stretched to 2 to 3 hours, especially for core practicals. Yeah, yeah. Check prior knowledge using a starter, introduction to topic with range of real and ideal examples, solved examples showing calculations, practice questions, exam style questions, and plenary. Excellent. Yeah, good. As I said, there isn't one right answer to this, but there are definitely some wrong answers, as it were. There's some really good suggestions here. And as I say, I find it really useful to have a framework to start with. You can start with a blank sheet of paper, but if you're not careful, you end up missing out some of the things that are important elements of a lesson. And I always use a sort of structure for a lesson plan, which just reminds me to think about them. You don't have to include everything in every lesson, but the thing which remind me, what have we already covered? So as Samantha just said there, checking prior knowledge, what have we done previously that leads on to this? What are we going to learn during today's lesson? How does that fit into the topic as a whole? Where is it leading to? So setting the big picture, and then where does today's lesson come into this big picture? And then what's the new learning for today? How are we going to check that new learning with solved examples, with calculations, with practice questions? Are there any experimental parts to this lesson? What will students be doing practically, if anything? Might be mini presentations, mini experiments, a longer experiment, might be students demonstrating something to each other or the teacher demonstrating something. So just to have suggestions that that you can build a lesson plan into, I think can be really useful to remind you not to miss some bases all the time, that within the core, you don't have to do every activity in every lesson, but within a series of lessons, you need to be tackling different types of learning to address the needs of learners who learn best with different styles, so that you're touching all the bases over a period of time. So I think it can be really useful to have a structure, knowing that you can move away from that, but it kind of reminds you each time, well, we haven't done this for a while, let's include an activity that does this, does that. So as I said, there's not a right answer, but I think it's useful to develop. It's something you can develop in your own style. You don't need to simply follow the textbook that you're using. Indeed, there are many reasons why not just following the textbook that you're using will improve the effectiveness of students' experience and learning. It's something you can follow as a framework, but move away from for different types of activities, so students get different experiences and it whets their appetite for learning. Thank you very much for those contributions, that's really helpful. Okay, let's go on and look briefly at types of support available. We're going to look at, there's online support, teaching and learning materials, past papers, mark schemes, examiners reports, teacher resource packs, and published resources, student books and lab books. I mentioned earlier on about the website, and here's a screenshot of the website. If I cut and paste, I can put the website address in for this into the chat. Okay, so there's a link to this web page, but rather than remembering long URLs, a much easier way is to use a search engine such as Google. Other good search engines are available. To use a search engine and just put in a combination of the words Pearson and advanced level or international advanced level, and it will take you to a page which then lists the subject in alphabetical order, and you can find physics. So it's just as easy to find in that way. Here's a screenshot of the physics top page, as it were, and you can see on here there are links to other things. This is not a live web page, it's just a screenshot of, so I can't use the live links here, but you can see all of the blue, bold blue lines with little arrows to the left of them are themselves hyperlinks. So under the bluey box which says course materials, you can see there are hyperlinks to pages which say specification and sample assessments, which would lead you to the two documents that we're using and made available on this course. There's a hyperlink to exam materials, 236 documents, because that's largely all the past papers and mark schemes and examiner reports from all the exam series that have happened in this specification, so you can access them all through there. And then also a hyperlink to teaching and learning materials, 34 of those, so booklets on different teaching learning styles, maths within physics, all sorts of other resources that are available. So it's a one-stop stopping off point to find all the materials that are available online there. But you can see also links to other things, training sessions, results support, grade boundaries. You can see a link to Irene, who I'll mention later on, our subject advisor. When you tick into the documents, by the way, particularly the exam materials, I will point out, if you click into exam materials, you'll see all the past papers and mark schemes and so on. The most recent ones, the ones from the series which has just passed, have a little padlock symbol next to them. There's a little grey padlock to the side, and if you click onto it, you can't open it. And the reason is it's padlock protected, and that's because of requests from schools and centres. Many schools use the most recent series of real papers as the mock paper for the next cohort of students. And the last thing you want, if that's the practice you use, is for your students, knowing that, just to go online, download the paper, download the mark scheme and learn that off by heart rather than learning the physics and tackling the paper. So schools have asked, can you padlock protect? Can you make them unavailable by just Google searching the most recent past papers? So all the past papers, ones which were a year, 2 years old, anybody can access, but the most recent ones are padlock protected. It's not meant to stop you as a bona fide teacher of Edexcel advanced level physics. It's not to stop you using them. You should have access to them. And the key to that is to talk to your exams officer. The exams officer in your school or your centre, the person who enters the exams and sends off for the number of papers you want and everything, the exams officer can not only access those documents themselves, but crucially, they can give you a login, username and password so that you can access the papers you're entitled to. Obviously, you can't access next year's papers. No one can get into those, but you can access the most recent past papers that you can access, your students can't. So if you've got some padlock protected papers that you see in there that you think, I want to be able to use this for my own mock paper or for my own teaching and learning, talk to your exams officer and get them to give you a username and a password. And it then means that then and in future, you'll be able to get into those documents which are padlock protected. So here's the website to go to as a sort of stopping off point for all the different types of support that are available online. And as I say, you can follow the link. Where to find the practical guide, that's within the teaching and learning materials. So on that page, on the sort of bluish box, a little way down on the right hand side, there's a teaching and learning materials, and clicking on that, there's access to the practical guide. Exemplar material. Exemplars, which are really useful, are marked exemplars with examiner commentaries. You can see the front cover of one here. They're available for both advanced subsidiary and full advanced level. And the exemplars are sets of student questions, questions from the most recent exams with real student attempts at those questions, some of them good, some of them not so good, and the marker's notes and the examiner comments on them. So you can get several examples of students attempting questions with what mark it was awarded and the examiner's comment on why it was awarded that mark and how it might have been improved. It's really good information. We'll be using some of these. If you're signing into module 2 tomorrow, we'll be looking at the exemplars in more detail and using them to get inside the minds of the examiners, because that's what they're really for. They're to look at how the examiners interpret the mark schemes. The Getting Started guide provides an overview of the Edexcel. I don't know why it says chemistry there. That's just a misprint, I think. Of all, it provides an overview of the specification, information about the content and assessment, gives a better understanding of what they mean for you and your students. The teacher maths support isn't a maths document, it's a physics document, but about the maths within physics. So it's a document about how to cover selected topics that students find difficult for the maths within the physics specification. Again, I think that's been wrongly cut and paste from a chemistry thing there, so because the things down there are related to the chemistry maths. But the document that's on the right is the one I'm talking about. There's a teacher maths support for physics, which links out the things which students find difficult in the physics part, the maths elements of the physics qualification, and suggestions on how you might cover those, teach them, introduce them, and so on. The practical guide, which I mentioned earlier on, as I say, supports you and your students through all elements of practical work in the specifications, and explains how the requirements for practical skills can be developed throughout the course using core practicals and other spec content. As you'd expect, it says something about each of the core practicals. It tells you which part of the specification the core practical is addressing. Quite a lot of information about how you might carry out the practical. So practical tips for setting it up, ways in which it can work, suitable alternative ways of working it if you haven't got that equipment, or different settings, so different ways of addressing it. Some really useful questions to aid learning. So questions that you can use with students to get into the heart of, do they understand why the practical is the way it is, rather than just, it's not just following a recipe of what are we doing, but why are we using this piece of apparatus? Why are we using this technique? So questions to enhance the learning from the core practical. And really useful, there are some examples of past paper exam questions based on that core practical. So when students have done the core practical, here are 1 or 2 exam questions to try out, to think, okay, this is how this might be used in an exam. So it's not just asking about the practical, but transferable skills learned from this practical, the way in which it's been examined in previous papers. Really useful guide. It keeps being added to, so I strongly recommend that you download it digitally and occasionally update it, because each time new ideas come in, it gets thicker and thicker, a bit like a telephone directory. And you can, as I say, you can update it and find more and more information. Scheme of work. I mentioned the scheme of work is broken up into units and topics, so there's greater flexibility for moving topics around to meet planning needs. As I say, it's in a Microsoft form, so it's fairly easy within Word or Excel to swap it around, to move documents, to change their order to match your own time. It includes recommended teaching time for topics and parts of topics, though of course it's adaptable according to your teaching needs. It includes classroom activities, teaching points, suggested teaching resources, and objectives for students at the end of the topic area, and examples of integrated transferable skills. So all of these are useful documents that you can download freely from that website I mentioned a few slides ago. And a mention of published resources. As you're probably aware, in addition to being an exam board, Pearson is a publishing company. They publish books. And amongst those books, they publish books to support each of the specifications. So there are textbooks, both student guides and teacher guides for each of the subjects that they offer. I should emphasize at this stage, and it's a really important point, you don't have to purchase Pearson textbooks to teach Edexcel specifications. We think they're good, you know, we believe in them. They match the specification and at the right level. But if you've transferred from teaching from a different specification, you may already have textbooks that you found really useful, that you're used to, that you're familiar with. And as long as you check that they cover the content and they cover it at the right level, there's absolutely no reason why you need to drop them in a skip and buy new Pearson textbooks. Okay, as I said, we think they're good textbooks, but as long as you're happy with the ones that you're using, you can certainly use other ones. You don't have to buy Pearson textbooks to teach Edexcel specs. Pearson have published 2 student books to cover the advanced subsidiary, the student book 1 there, and the second, the IA2 courses that make up to the full A level, the student book 2. And there are also teacher guides along with them. So they are, and if you want to look at the textbooks, you can go again to the Pearson publishing website, which you can find a link from that physics page to look at. You can either search for Pearson publishing or go from the links from the physics page and find out what's available. If you buy the paper textbooks, the printed textbooks, it gives a code within there, so students having a textbook can also access the digital version, the e-book, which has within it interactive questions, and so you can do some online learning as well. So it gives them access to the digital version as well as the paper textbook. I think it gives a 3-year license into it, so you can use the book to access the digital version. Pearson have also published a lab book, which you can choose to use or not for laboratories. It's different teachers will make different decisions about how students record their learning within experimental techniques, but they have produced a lab book, which includes within it the core practicals and space for students to be able to record findings within those. It contains instructions for each core practical, together with some questions to ask. As I say, students can enter their results or observations directly into the book. You might find it's cheaper than photocopying the material for each individual practical. I mean, it holds it all in one place, which can be useful for revision. So it's worth having a look and seeing whether or not it meets your needs. Okay, I mentioned Irene earlier. Irene is a source of gold dust. She is our science subject advisor, and she is the place to go if you have any questions at all about this specification, or in fact any of the science specifications. You can see the various ways in which you can contact her here, the email address there, teachingscience@pearson.com, or the Twitter account, or the telephone number. If Irene doesn't know the answer to your question, in my experience, she knows the answer to most of them, she will know someone who does. So if you send her a question, email her a question, if she doesn't know the answer, she'll direct it to someone within the company who can. I think I'd also encourage is contacting Irene to sign up to her email update service. She doesn't send out adverts on the email update, but it's a regular service where she can send out any changes or updates to deadlines and things like that that happen relevant to the specification you're interested in. It was specific. It was especially helpful during the time when we were going through the pandemic and different changes, because different parts of the world had different shutdown and lockdown situations and different effects of those on exams. And throughout that, I was able to keep different centres informed of what changes had happened in their own particular area with the specification they were entering. You know, what had changed with regard to the exams and the exam conditions and coursework deadlines and all these sorts of things. So it's a really useful thing to sign up to. It means you don't have to keep going back to the website to see, has anything changed in my specification? You can be informed when it's been updated. So it's a really useful link. As I say, Irene is excellent at what she does. I strongly recommend that you get in touch with her.